Technology demonstration missions, taking the next step in deep space navigation, spacecraft propulsion, and deceleration. Can a giant inner tube slow spacecraft for safe atmospheric entry? Will solar sails propel satellites through space? Check your space watch. It's time to find out how it all works on NASA Edge.
Welcome to NASA Edge.
Hey, I was looking forward to this new look, but it's not what I expected.
It's kind of rough, isn't it?
Yeah, it's kind of rough around the edges.
What do you think?
I mean, it's intimate, it's nice, it's close quarters. I kind of like it. I don't have any problems with it. I think it's gold.
What are you talking about?
The show, the new look, this whole setup, it's awesome.
No, we meant your beard.
Yeah, that's what we're talking about.
That's what we're talking about.
No, it looks rough, but it's actually smooth.
You're talking about the studio.
I'm talking about the whole motif we have going here for our interaction.
Now this looks pretty cool.
Yeah, this is actually awesome.
Wait, are you saying the beard's not cool? All right, well, verdict's out.
Move on.
It is a demonstration. It is a fashion demonstration mission.
Is that fashion?
Or
grooming demonstration.
Grooming demonstration.
Is this a technology demonstration?
Actually, it's a technology withdrawal. I'm actually not using any razor or anything or product. I mean, I'm going straight natural.
So what we're gonna so the plan here is that we're gonna be discussing several technology demonstration missions, which is the focus of today's show.
And I actually have to say something. On the last technical demonstration mission episode that we did, I was knee-deep. I was mired in an investigation
on Medley.
Of Medley. Mm-hmm. Yeah, and I got to say, by the way, that was very successful, and I did a great job. In fact, it's now the standard, the de facto standard for all investigations across the agency.
I just don't think that was the case.
Yeah, well, we agree to disagree.
Okay.
Well, I'll tell you what, since you are in that pre-investigative role, we'll let you start off. Since we covered 3 TDMs this show, let's talk about what you covered.
Okay, well, what I was looking at was the Deep Space Atomic Clock.
Or DSAC.
Or DSAC. When I first heard about this mission, I immediately was fearful. I thought some kind of atomic disruption in the space-time continuum might occur, which would be bad. But it turns out that that's not the case at all. This is a very essential part of all spacecraft for flight and everything else. So I was excited to actually get out to JPL and talk to Todd Ely and actually get into the nuts and bolts of what is the Deep Space Atomic Clock. And Todd, I have to confess right off the bat that atomic clock technology is not exactly in my wheelhouse of expertise. So I was wondering if you could just explain real briefly, what is an atomic clock and how is it used?
Sure, let's start with use. We all take advantage of atomic clocks today, even though we might not know it. The GPS system that we use to navigate on Earth is based on atomic clocks. There's an atomic clock on board each of the GPS spacecraft today. Usually, the size of a refrigerator, and what we're doing with this technology development is to reduce those refrigerator-sized atomic clocks and make them smaller, more suitable for space flight. And the way the clock works is we're utilizing a feature of nature and atoms and their ability to resonate at particular frequencies very precisely. They're like a tuning fork, but we're using that atomic resonance to measure that frequency and compare to an oscillator that's generating a frequency or time signal to correct that.
So what's the purpose of that? Why do we need that for our spacecraft?
Sure, so we need to navigate. We need to know where we're at. And the way in which we navigate today is we measure how long a signal takes to travel from the tracking station to the spacecraft and how fast the spacecraft is moving. And to be able to do that, we need a very accurate frequency source and time source. Since today's spacecraft clocks aren't very accurate, today we have to send the signal up, turn it around, and measure that time delay and that speed. With the Deep Space Atomic Clock, we're able to put that in a spacecraft and we no longer need to turn that signal around. We can either send the signal from the spacecraft and measure it here at Earth, or, thinking a little forward in the future, measure it on board the spacecraft for the spacecraft to use for navigation.
If this is successful, if you actually add them to spacecraft, how will we benefit from having this technology on board the spacecraft?
For deep space navigation, it enables a more precise measurement. It also allows us to collect more tracking data, and so more data, better navigation. By being able to put it on board the spacecraft, if we have time-critical events where the spacecraft needs to know where it's at and how fast it's moving, at the time that it's needed, it allows that to happen. Thinking a little bit closer to home in GPS, the Deep Space Atomic Clock is an excellent candidate to replace the existing atomic clocks on board GPS today. It's more accurate and precise than those atomic clocks, so it has the potential to improve GPS performance.
No more recalculating. This will be so when I'm driving, I can actually get to my destination without having to pass it and then turn around.
Exactly.
Awesome. Well, I love this already.
There are some ideas to take this technology and really miniaturize it. So the version of the clock we're building for our demonstration, it's maybe the size of 2 milk cartons. But there are ways which we could reduce that even further. The key component of the clock is this thing we call a trap, where we actually confine the mercury ions and measure that resonance that I talked about earlier. That trap is about this big, maybe an enlarged starburst package.
Nice.
But there are versions of that trap that get down to maybe a few sugar cubes.
Nice.
Very tiny.
Now, it's interesting because you mentioned future there, and I'm just wondering, are there any plans to use the Deep Space Atomic Clock for time travel, possibly?
Well, I don't think we could use the clock for time travel, but we'd know how far we traveled in time if we were able to do time travel.
Okay, so there is hope. We might be able to find a future application for that. I got to tell you, I was really surprised. I didn't know how much we relied on atomic clocks for navigation.
Right.
I mean, you think about it, it's obviously difficult for boats. That's why they use them. But for ships being in, or for spacecraft being in space, it's really important to know exactly where you are. So really good technology.
But the cool thing about that is how small can they get the technology? How can they miniaturize it?
Yeah, double pack of Starburst.
Yeah.
I was sitting there like, yeah, how do you get something from a refrigerator down to
snack size, basically.
Snack size.
You're moving from a meal to snack size with all the effectiveness.
And is it possible one day that you can actually see an atomic clock the size of a microchip?
Well, I wonder because, everything's getting smaller. And if it's in every single spacecraft, pinpoint accuracy.
Right.
And like I said, I long for the day where the GPS does not ask me to recalculate or to turn around, do a U-turn in an uncomfortable spot.
starts to buffer when you're in the wrong part of the neighborhood.
Oh, yeah.
You're like,
That can be bad sometimes.
Yeah.
Hey, I tell you what, you had a chance to go to LaGuardia to talk about solar cell technology.
Yes, I talked to the company CEO, Nathan Barnes, about the solar cell demonstration, and we stood in their facility, their workshop, and just talked about this technology and what's coming up with their mission. I'm here with Nathan Barnes, the project manager for the Solar Cell Demonstrator, or SSD.
Yeah, that's a little boring name. We like to call it the Sunjammer Project.
Well, give us a little bit of backstory on the name Sunjammer.
Sure. Sunjammer is a short story written by Arthur C. Clarke, and it was published in the 1963 Boy's Life. We contacted Arthur C. Clarke's estate and asked him if he wouldn't mind us using the name of the story for our project. The story is about a solar sail yacht race taking place far in the future, and it seemed very fitting.
Now, you guys didn't just come up with a solar sail. You had to have been working on this for some while before you got involved with NASA.
Very correct, very correct. We've been studying solar sails and, writing designs of solar sails and papers about solar sails and so on and so forth for many years.
What is the need for this technology?
What one must think about is that they're another form of propulsion, right? We have rockets. Everyone knows what rocket motors are. But solar sails are another form of propulsion, just like them. Now, they're a very low thrust form of propulsion, but they're a perpetual form of propulsion, right? They keep going. They will just continually be thrusted by the light of the sun. So there's no need to carry consumables. There's no need to throw stuff out the back in order to push us forward. Because of that, it will enable a whole host of unique missions that are specifically tailored to solar sails.
What kind of weight are we talking about with this solar sail?
We're trying to conform it to a standard that says that it needs to be about 28 inches by 28 inches by about 38 inches. So we're roughly the size of a dishwasher or a washing machine in your household. Now when we deploy, we're huge, right? We're 1,200 square meters, which is roughly a third of an acre. We're very low mass. We're targeting that once we've jettisoned a handful of consumable items, our solar sail is in the neighborhood of 35 to 40 kilos. So we're incredibly large, 1,200 square meters, and incredibly lightweight. And those two things, Newton tells us, force equals mass times acceleration. Therefore, if we increase the force by making the sail larger and collecting more of that photon pressure, and we decrease the mass by pinching every penny and removing every bolt that we don't need, then we'll have a higher and higher characteristic acceleration, which really defines the performance of our sail and tells us where the sail can go to and what it can do for us. Now, for this particular mission, we're going to take our sail and demonstrate that we can use solar sails for advanced storm warning. Currently, NOAA monitors coronal mass ejections and informs folks that are interested in the data of incoming solar storms, solar flares. And they monitor this at the L1 point, which is roughly 1.5 million kilometers from the Earth towards the sun on a line that connects the Earth to the sun. With that station, they get roughly 40 to 45 minutes of warning time. And that's good, that's great. But we'd like to do better. We'd like to give them more warning time. So what we want to do with this solar sail is fly to and maintain a position that's roughly 3 million kilometers from the Earth instead of that 1.5. So 3 is twice 1.5, means that we'll get about 80 to 90 minutes of warning time for the ground operators.
How does it maneuver? How does it work in space?
Yeah, very good question, right? You know, the way we're propelling ourselves is with this solar radiation pressure. Our square solar sail actually has small little solar sails out at each corner of the solar sail. Those little solar sails can be tilted and twisted in order to increase or decrease the amount of solar radiation pressure they're getting at each corner. And you could imagine if we turn off the pressure on this side and we increase the pressure on this side, we can make the sail rotate. It's very similar to the control surfaces or ailerons on an airplane.
When I think about this large sail that's going to be put into such a small box,
sure.
I'm thinking this has to be some lightweight material.
So our solar sail is built of a whole host of very lightweight and very cutting-edge materials. The material that's most visible, most recognizable is the material that the sail area itself is made of. Now I have a little piece here with me. Our sail area is built of Kapton, material, and it's incredibly thin. This is 5 microns thick, which is many, many times thinner than a human hair. It's been coated on this side with a blackened chromium. The chromium is so thin that you actually see mostly the yellow of the Kapton coming through. On this side, this is coated with an aluminum material. When the photons strike this is the side that reflects them back towards the sun or wherever they may go to. And this is the side that actually faces the sun and propels the sail. Now, the next step beyond that, this is
Saran wrap.
This is
Saran wrap.
This is 0.9 micron mylar. This is incredibly difficult to work with. But we have worked with it, and we've built sail-type materials out of it, right? This material is so gossamer and so lightweight that now it's just stuck to me, right? This is probably the direction of sails in the future.
I want to know, who is your nemesis?
Our nemesis?
Your nemesis.
My nemesis?
Yes.
I don't know that I have one.
Superman?
No, I think that's okay.
Superman's okay?
Yeah, I think so.
Your sole mission of the solar sail is not to block out
Absolutely not.
The light, the power from the sun, so that Superman will not have his powers.
No. You know, for one thing, our sail's pretty small compared to the sun.
Okay.
But we did have some notions of when we launched the sail. Maybe we could make it do this a couple times to wink at the Earth, you know. But
you'd be able to see that too, right?
Yeah, well, you know, if we were close enough, we probably could. But the physics, I think, probably won't work out for that to happen.
You're looking at this sail, and you're looking at the technology to say we can make this bigger, we can go
much
further.
Bigger, much bigger. So one of the things that we're actually kind of studying with this, and it's a very far out idea, a very far out project, is using it to kind of beam some sunlight down to the Earth on the other side of the Earth when the sun's not on it, right? So we've studied and we've worked with a couple folks, and we've written a proposal recently to study that and see if there's any merit to it. But it's a good thing, right? No nemesis. That's helping humanity there.
Okay, all right. Was it me, or did Nathan look like Lex Luthor?
I thought that someone's going to bring a case and open it up and there would have been kryptonite in there.
Oh, you know.
The resemblance was uncanny.
Hey, real cool guy.
But he didn't know Superman.
Okay, there's some debate about that.
Yeah, it was the way that I rolled out the questioning.
No, if he really is a supervillain, then he's obviously not going to admit that on camera. I think he was sort of playing close to the vest.
That's true.
That is true.
And I mean supervillain with all due respect, by the way. It's the first one we've had on the show.
Who had my camera on that shoot?
That shoot, that was me.
Why didn't you tell me I had like a piece of macaroni on the bottom of my lip?
I didn't see one.
Oh man, I'm sure Ryan is going to show like a circle around it right now.
Now, Chris, for the third technology demonstration, tell us a little bit about what you looked into.
Yeah, I had a chance to talk with Ian Clark at JPL, and his technology was LDSD, or Low Density Supersonic Decelerators. So what is LDSD all about?
Low-density supersonic decelerators are describing a class of decelerators, aerodynamic decelerators, that we are developing to enable the next generations of missions to Mars. These include large robotic class, like what we just landed a year ago, but bigger, that we want to land at higher elevations than we've previously been able to get to before.
So what are the new technologies that we're looking at now?
Well, there's 3 new technologies that LDSD is developing. 2 devices are things we call supersonic inflatable aerodynamic decelerators, or SIADs. These are similar to parachutes in that they are pressurized devices, but rather than having an opening at the front, they are closed volume devices. These are things that are inflated at speeds much higher than we typically use parachutes, and they're more integrated to the vehicle. So they're actually attached at the front of the vehicle to change the shape and the size of the vehicle, rather than being deployed behind the vehicle. The other one is a new, improved, larger supersonic parachute, the biggest parachute that will have ever been flown at the conditions that we're testing and that will ever be used at Mars. We can take a parachute that weighs only 300 pounds, but it will generate 150,000 pounds of drag. Just an enormous aerodynamic load.
Very efficient.
Extremely efficient. But the basic parachute design that we've had is a design that we thought we could improve on. And we're improving on it in a couple different ways. The basic shape, how the geometry is laid out, we can improve on. We actually understand the aerodynamics a little bit better now.
Okay.
We can take advantage. The other thing that we can do is just make it bigger. Parachutes are very fickle devices, particularly supersonic parachutes.
Right.
When we have to use them like we do at Mars, it's behind a very large, blunt vehicle. That vehicle is screaming through the atmosphere. It's punching a hole in the atmosphere. All the air is rushing in behind it to fill the vacuum that it's creating.
Right.
And that creates a very turbulent, very unsteady environment for the parachute to live in. So you need a very kind of particular parachute. We're going to develop a new shape, and we're going to make the parachute bigger. The bigger it is, the more drag it can generate. The more air it encompasses, the better it's able to slow a vehicle down. The bigger the vehicle you can have in front of it that you're trying to slow down.
Now you talk about a bigger parachute. How much bigger than the current technology that we're using now?
Well, MSL parachute was about a little over 60 feet in diameter.
Okay.
We're looking at parachutes that are over 100 feet in diameter.
Wow.
So area-wise, we're about 2.5 times the area and 2.5 times the drag of the MSL parachute.
You developed another technology to actually help release that parachute from the spacecraft?
We did. Again, when we test the technologies at this scale, nothing is coming easy. The way that we typically deploy parachutes is something called a mortar. It's like a giant cannon. When you get to parachutes the size that we're testing, you can still use mortars, but the difficulty is the mortar wants to sit in the middle of the vehicle because it generates a very high reaction load, a lot of force. And if that force is put off center line of the vehicle, out on the perimeter, it can generate a torque, and you can start to tumble the vehicle. So we're going to use another inflatable decelerator that's deployed and inflated behind the vehicle, much smaller, but that can be shot using a mortar without tumbling the vehicle. And we're going to use that to pull the parachute off the back of the vehicle. But this one is a very particular design. We had to go back to something called a balut. It's a device that originally was developed in the early 1960s, and that we've gone back to the literature and said, yes, they tested some small ones, we're going to build a very large one, and we're going to use that. And that's what we're doing. We're developing new parachutes to replace the one that we inherited, bigger, better performing. And we're developing something called SIADs, these inflatable devices, things that are packed in very tight crevices, periphery of the vehicle, that we can inflate and deploy at speeds even greater than what we deploy parachutes. And there's lots of different kinds. Part of LDSD, we're developing 2 flavors of SIADs. Something we called SIAD R, and the R stands for robotic, and SIAD E, or exploration. And the 2 flavors are really targeted at different mission classes. So robotic would be sort of the next evolution of the Curiosity rover, something a little bit bigger. The exploration is starting to look at, okay, what if we do want to start landing the 3 or 5 or 10 ton payloads on the surface of Mars. That side looks very differently and behaves very differently than the one that we need for something that's just a little bit bigger than Curiosity. So the Dash R, it looks like an inflated donut. It's a device that we can inflate to moderate pressure, about 4.5 psi, or a fraction of what you inflate your car tire to. But even at 6 meters, in 4.5 psi, it behaves very rigidly. And we like rigid objects because we understand how they behave. You don't have to worry about them deforming under different loads or interacting in their environment differently. Because it's rigid, it scales very well. And we know how to work with things that scale. We like to build little small 6-inch diameter models or 2-inch diameter models and put them in a wind tunnel and test them and understand the aerodynamics. And we feel comfortable, because they're rigid, because their shape is the same, that we can take them to 4.5 meters in diameter and that they will behave, that the aerodynamics of that 4.5 meter device will be the same as the little 2-inch or 6-inch model that we tested. But you can only go so far with that. 6 meters is about as big as we think we can build something and still have it behave rigidly. And eventually we're going to have to tackle the problem of what it means not to be rigid. So we went with an entirely different device. It's called an attached isotensinoid, and it's much more flexible, but it's integrated to the vehicle. It's right up at the front, and it basically changes the shape of the vehicle and also makes the vehicle look bigger to the oncoming flow. So think about the ram air scoops that are on the top of your muscle car, pulling in air at 150, 160 miles an hour. Well, we have similar scoops on the side of our side E, that are pulling air at 2,000 miles an hour. That air comes into it, helps inflate, helps give a nice, good shape to the vehicle, and helps generate that shape that's necessary to slow our air shell down.
I mean, you have to develop a piece of material that's actually will be able to withstand that. So what kind of materials are these going to be made out of?
Parachutes are made from materials similar like what your camping tent might be made of, like nylons, for example. When we build SIADs, we need things that are stronger. Because we're using them at higher speeds, they see more heating and they need to be a little bit more temperature resistant. So we actually have 2 different materials that we're working with. One is Kevlar, very similar type of Kevlar to what's used in bulletproof vests. It's extremely strong, very flexible, and still can be made very lightweight. And so that's what we build the SIAD R out of. For SIAD E, we're using a slightly different material called Technora. Very similar looking, very similar behaving to Kevlar, just has a little bit different properties that make it more amenable for something like SIAD E. But otherwise, these are very thin materials, thinner than the fabric on your shirt, for example, very lightweight.
What a great way to wrap up the show on a great technology with LDSD and all the 3 technologies we talked about today.
And it still stuns me that just how much development there is to slow things down. The balloon, the inflatable idea, that's just really cool stuff.
New age space brakes.
Yeah, I mean, it's definitely another, like the front brake on a 10-speed or something versus the rear.
From clocks to solar sails to decelerators, we covered it all.
And what's next? Next mission, K-10?
That's right. We had a chance, Franco and I had a chance to go out to NASA Ames to cover the K-10 test where an astronaut from space station actually operated the K-10 rover on the ground.
In conjunction with a sleep deprivation study.
Yeah, we were out there pretty early in the morning covering the test through the morning into the afternoon, but it was a good time, and I think you're really going to enjoy the show.
Can't wait.
You're watching NASA Edge.
An inside and outside look
at all things NASA.
Love the new look in here.
Hey, are you keeping the beard?
I am keeping the beard until I get complaints.
Okay, real. It actually looks pretty good.
And it's real. I did not apply this morning.